So yeah, I think today we're going to be going over initially for about like the first half an hour. We're trying to accomplish about 70 to 80 slides with a quick overview of all the different components that are interacting with one another within a blockchain system. From there, the last 30 minutes or so, we're gonna get some test ether, and we're going to get MetaMask, and then we're going to deploy the first smart contract onto the Ethereum test network of our own choosing, which in this case we'll probably deploy it onto the RIMP testnet. So to start out this whole story, right, we have to really think about this whole story starts from Bitcoin, right? And we have to remember that the idea of electronic money, though, did not really start with Bitcoin. It's been around since about the 1980s by a computer scientist by the name of David Chaum. And there are two different fundamental eCash system issues that normally need to be addressed. The first being accountability. So the eCash or the electronic money needs to be it can only be spent once by the owner, right? So we can't have a double spending on this sort of digital asset. And the second is anonymity, right? So if I go to the 7-Eleven store right now and I spend some dollar bills, there's no easy way for you to track back into that I actually spent that money. So before Bitcoin, we had DigiCash, which was from David Chaum. We had B-Money, which was from Wei Dai. We had BitGold from Nick Szabo, as well as Hal Finney, a really famous computer scientist, wrote the RPOW, Reusable Proof of Works, in 2004, which I believe was private code at that time. So somewhere around 2008, there was a white paper that was published, and it was Bitcoin, right? Bitcoin, a peer-to-peer electronic cash system. So it was initially introduced in 2008, but the practical implementation was released in 2009. And overall, what is Bitcoin, right? Bitcoin is a decentralized peer-to-peer open source protocol that solved the Byzantine generalist problem in an unreliable network without a central authority, right? So the main innovation overall is that we are able to solve the double spending problem in a decentralized manner. So the founder of Ethereum, we're not sure if it's a he, she, they, but they remain actors, and has basically disappeared. So we brought up Bitcoin because blockchain is the underlying technology that powers Bitcoin. It's really interesting to note that I mean, the term blockchain was never used in the original paper. It was always chain of blocks, and then later on down the line, the term blockchain emerged over a span of time. It's pretty funny over here as well. I'll mention one thing, which is that the first tangible asset of Bitcoin was bought. It was a pizza on May 22nd, 2010. And it was a $25 worth of pizza, and this individual spent about 10,000 Bitcoin on it. And 10,000 Bitcoin is equivalent to about $98 million right now. So that's a lot of money. So Bitcoin, so blockchain is the underlying technology that powers Bitcoin. But what is a blockchain? So a blockchain is a peer-to-peer distributed ledger that is cryptographically secure, append only, immutable, or at least really hard to change. And it's only updatable via consensus agreements amongst the peers that are on the network. So we're going to look at these four core technological elements. The slide's a little bit wrong at the top, but we're going to take a look at what is a distributed ledger. We're going to take a look at what does it mean when we say cryptographically secure. We're going to talk about peer-to-peer networks and distributed consensus. So according to Google, a ledger, right, is just a book of collection of financial accounts of a particular type. And in our definition, we said blockchain is a peer-to-peer distributed ledger. So essentially, a distributed ledger is essentially a database shared on a distributed system. And a distributed system involves a set of computers that are passing messages to one another and coordinating to accomplish a common objective. So, and we use this sort of double entry bookkeeping that was invented by the Italian bankers in the 13th century to make sure that we can add up our books at the end, right? If we only was storing one number in our ledger, there would be no way for us to figure out discrepancies within the data. So it's one thing to remember, though, while all blockchains fall into the category of being a distributed ledger, not all distributed ledgers are blockchains. Distributed ledgers do not necessarily need to keep the ledger growing. So a good example of a distributed ledger would be like R3 Corda. So you're going to hear me say blockchain a lot of times over here, but at the fundamental core, right, every blockchain contains a next generation database structure called a blockchain, right? And as the word states in the simplest form, the blockchain is a chain of blocks. Each block has a set of transactions that have been validated by peers or nodes on the network, right? So each block contains a group of transactions that have been digitally signed. And really quickly over here, when I'm referring to the word node, right, I'm essentially talking about an endpoint that can create, store, receive, and send data to the distributed network. And to simplify that even further, right, I'm talking about essentially like your phone, your computer, some random server in the cloud, right, that is able to connect to the distributed network. And a peer is a node that is connected to another node on the network. So a really good analogy over here would be we are all people, right? But me and Paul, we are friends, right? Or peers, right? So we are all nodes, but when we're connected to one another, we are peers. So overall, this database structure is stored across the overall network on each of the nodes. And we use a distributed consensus mechanism to make sure that all the nodes are in sync. So now we're going to talk about cryptographically secure elements. All right. So when we say cryptographically secure in our definition of a blockchain, we have to really ask ourselves, how do we trust in a trustless environment, and what is cryptography? All right, cryptography is the science of making data secure in the presence of adversaries. It's been around for a long time now, and in the early days, people used techniques such as the Caesar cipher, where they would essentially move, or they would shift the letters in the alphabet by X number of letters that only the recipient would know, and then they would also create the key so that they can decipher the code essentially. So you can see it's a quick little example over here of like hello moving into core. So cryptographic algorithms can be categorized into three different classes: symmetric algorithms, asymmetric algorithms, and hash functions. Just to keep it simple, since we're going relatively quickly, hash is equivalent to the fingerprint data.
That's what I
Wow. Sorry, is there someone on the phone? While encryption is essentially the safe blocks for the data, right? So essentially, it is the actual data itself.
Peanut butter, honey, healthy.
Would we be able to mute this individual, please? So the process of cryptographically securing your data involves two main steps, encryption and decryption. And ciphers are the algorithms that are used to encrypt and decrypt the data so that if it's intercepted by any adversaries, the data is meaningless. So very simply over here, right, encryption is scrambling the information so that only the intended recipient can access it. And decryption is the unscrambling of the information so that unscrambling the encrypted information in order to access and use it. So we covered, so now let's cover symmetric cryptography. Right, so symmetric cryptography is sometimes known as shared key cryptography or secret key cryptography. Right, so essentially what this means, if you look over here, is that you use the same key to encrypt and decrypt the data. And before there's any exchange, right, since it's the same key, there has to be some sort of exchange of the key, or it has to be agreed upon ahead of time. We won't go too deep into symmetric ciphers, but essentially there's two main types of symmetric ciphers, stream ciphers. Some common examples are RC4 and A5, and block ciphers. And some common examples for that is the data encryption standard, DES, and the advanced encryption standard, AES. AES is most commonly a symmetric key algorithm. It's used to encrypt your hard drive, as well as securing your connection to a HTTP website. And now we're going to cover a little bit of asymmetric cryptography, or public key cryptography. So public key cryptography essentially uses two keys, uses separate keys for the encryption and decryption process. And the public key is what's shared openly, and the private key is what's must be kept secret. So, and we use asymmetric cryptography to essentially, we use it in two different places. One, we use it to digitally sign our transactions, and two, we use it to generate our essentially our identity on the blockchain, right? So, I'd like to give you guys another analogy, right? Like, so overall, right, you have your public address, or you have your address to your house, right? And that's like what you share to other people if they want to send you something. But then you also have your mailbox key, right? And your mailbox key is something that's private. You're not going to give it to anyone else, and only you can use it, essentially, right? So your public key in this case, right, is going to be your public address, and your private key is something that you're going to keep secret, so that you can sign your transactions. So digital signatures are very much so like normal signatures. They're used to verify the integrity of information. They're used to also authenticate the origin of a transaction submitted to the blockchain. And this process right here relies on public key encryption, or symmetric encryption. So essentially what happens is that to prove a piece of data is authentic, the sender's private key is processed through a digital signature algorithm with a hash of the data using ECDSA algorithm, elliptic curve digital signature algorithm. And the output is the signature of the transaction that and it's going to be different every single time for every single transaction, but it can be verified by a public key, right? So to simplify this process, you're on your computer, right? You want to make a transaction with the blockchain network. So you're going to sign your transaction, you're digitally sign your transaction with your private key and submit it to the blockchain. And then the overall network can essentially verify that transaction by using your public key, essentially. So now we're going to talk about cryptographic hash functions. So once again, hash is the hash functions, very simply put, is the fingerprint of the data, right? So when we send data, and it can be of any input through a hash function, it's going to produce a specific fixed length unique hash. Given an input, they will always have the same output because these algorithms are deterministic. As well as this process is a one-way. Sorry, this is also a one-way process, right? You cannot decipher what the original data is from the hash, but you can verify the data utilizing the hash. So the beauty is that it can be computed extremely quickly, and a slight change in the input results in a significantly different output with no relation to the input, right? So, and that's what we call the avalanche effect. So there's few properties of cryptographic hash functions that you should be aware of, right? The first is that they are pre-image resistant. So when you are given an output of hash of X, it is very difficult to guess what X is, right? It's also second pre-image resistant. So essentially, given your fingerprint, it's very difficult to find someone else with the same fingerprint. So essentially, given x, it is computationally hard to find some other value as x, right? There's no way, there's no patterns that you can use very easily to find something. And the third is collision resistance, right? So it's computationally difficult to find x and y, such as the hash of x and hash of y are the same. In Bitcoin's case, they use the SHA-256 squared hashing algorithm. So let's just quickly take a look at this, right? We're going to go to this website right here, anders.com/block, anders.com. Okay, actually, we'll go to anders.com/blockchain. And we're going to put over here some data, right? So you say hello, right? And then you can see over here we have our hash. And essentially, if you guys type in hello as well on your computers, the hash should be exactly the same. So coming back to blocks, right, and where we use this right here, each block is linked to, has the hash of the previous block, and that's essentially what secures this data structure. So you see over here, this is block 51. It has its own, it has the proof of work, it has the previous block's hash, and then it has all of the transactions. And so essentially this creates a link to one another. So I'll demonstrate that over here really quickly. So you have some sort of block, it's got a hash, you gotta mine it, and then it should show up. And then let's click over here to a blockchain, right? So let's add in transaction 1, 2, 3, right? Notice over here, this is our first block, so essentially it's our Genesis block, and there is no previous, this is 0, 0, 0, 0, 0. And then we click mine. Come over here, we add in transaction 4, 5, and 6, and let's click mine. And let's go to block 3, and let's say transaction 7, 8, and 9. So notice how each one of these blocks, right? So it contains the previous block's hash, right? So this one right here has the previous one 0001, which is the hash over here 0001. This one has 000F, and over here you can see we have 000F. Now, what I'm trying to show you guys over here is that if anyone tries to change any of the data in the previous blocks, it will immediately break the rest of the chain, right? So if I even add in one extra letter, right, you'll notice that the hash has completely changed, and essentially all of the blocks afterwards are now become invalidated. So, and I highly recommend you guys, if any of you guys are interested, there are some tutorials online where you can write out your own blockchain. There's a really good pack book that even introduces it in like the aspects of networking as well. So it's very interesting. Highly recommend taking a look at it. But you can see over here, I mean, obviously this is not a real, like this is not what an actual blockchain would look like, but our block contains an index, timestamp, all the transactions, a nonce, a hash, as well as the previous block's hash. So before we talk about wallets, right, we talked a little bit earlier about symmetric cryptography, right, and we said that for our identity, we need to have our public and private key. Our private key is what we're going to use to essentially digitally sign these transactions. Now, where are we going to store these keys? And so the answer to that question right there is wallets. And we'll talk about like the physical types of wallets, but before that, we'll talk about the different type of technical wallets that you can create. But overall, wallets, they can contain one or more private keys within them. From your private keys, you can derive the public keys. Overall, we use an algorithm to create a public key from our private key, right? And the wallet address is generated from the public key. So first type we'll talk about is non-deterministic wallets. So non-deterministic wallets were created during the first implementation of the Bitcoin client. The keys are derived randomly, and so there's no association with one another. And there's essentially no way to determine how they are derived. So start with a random number and convert that into our private key. Using our private key, we generate a public key. Using our public key, we generate a wallet address. And there are two different types of deterministic wallets, this sequential and this hierarchical. So we'll talk first about sequential. So essentially it starts out with a mnemonic phrase or seed, which you guys are going to see when we download MetaMask in a few minutes. And it derives the master private key from the mnemonic. And essentially what it does is it adds in a counter, and so it adds in a counter and incrementing value when generating a new private key. So imagine like there's a counter and it's continuously incrementing for all the new keys that are being generated. But it isn't a flat list, right? So using those inputs generated, we can generate new private keys, and those keys can be used to generate a new address. And we can also use the mnemonic as a backup to recover the private key, or essentially the master private key. And then we have hierarchical deterministic wallets. So long story short, essentially the data is stored in a tree manner. So all keys in the tree can be generated. Oh, sorry, all keys in the tree can generate any number of keys underneath them. Right, so just imagine a tree, and you can just keep generating keys underneath each leaf node. So we have hot wallets, right? Hot wallets are essentially wallets that are actively connected to the internet. Exchanges, mobile wallets like Coinbase Toshi that's on your phone, or a desktop wallet are all hot wallets. Highly don't recommend keeping any sort of significant amount of cryptocurrency on a hot wallet. It's more for like your day-to-day use. And the second is cold wallets. Cold wallets essentially are crypto wallets that are not connected to the internet, and they're safe from any sort of hacking attempts, right? So you can have desktop and mobile wallets. So I recommend you guys take a look at a few of these right here. On my phone, I use Coinbase Toshi wallet, or it used to be called Toshi wallet. Now I believe it's called just Coinbase wallet. It's pretty nice, good UI. A few things I like about it. One, it has a Google Drive backup for the keys. Obviously, you don't want to keep any sort of real money on it except for like the day-to-day transactions. But yeah, it's pretty nice, and it also has a DApp browser built into it, so it's worth taking a look at. And then we have online wallets, right, such as Coinbase, Gemini, but you don't actually own your keys. We have paper wallets, where you can write down your private key on a piece of paper and print it. There's a professor who once told me always create 2 copies of your private keys, then cut each copy into 3 separate pieces, and then hide them all in separate places. Obviously, you have to have significant amounts of money for this to actually make sense. But and the third is we have hardware wallets. So 2 things that you guys can take a look at is you can take a look at the Treasure and the Ledger. And the nice part about these is that it is cold storage, but you can easily flip it and have your wallet connect to the internet in case you want to transfer some money to an exchange to sell it out, or transfer some new coins into the ledger itself. So coming back to the interacting elements, we'll now talk about peer-to-peer networks, right? So our state overall, right, of our blockchain, which is stored across many different nodes on our peer-to-peer network. And our peer-to-peer network allows for peer discovery and data transmission. Using peer-to-peer networks, it allows us to turn the traditional client-server architecture of the web into the peer-to-peer architecture of the new decentralized web, in which every node is the client and the server. Note that the differences between distributed and decentralized, or decentralized, there is no authority on the network who has more authority over another. Or essentially there's no central controller on the network, and all of the participants or nodes on the network communicate directly with one another. And using this sort of networking, we're able to diffuse information silos and remove single points of control, vulnerability, and failure. So now we'll talk about distributed consensus, right? So essentially, we've got our database. We understand how they link together using cryptography, and then we understand as well that this distributed ledger is essentially being stored on this peer-to-peer network, right? But how do we get consensus across all of these nodes on the peer-to-peer network? So Dr. Arthi Baliga said, a blockchain-based system is as secure and robust as its consensus model, right? So consensus, in a network where there are distrusting nodes, we require consensus to determine the final state of the data or the single version of truth, right, before we have a state transition. It provides us a way to compare one node to all the other nodes inside the network to confirm that we have the correct data on that specific node. Consensus is also a group of algorithms that we can use, or is a group of algorithms that we use to create a voting process on the overall network. And determining consensus across multiple nodes is known as distributed consensus. Overall, due to some of these blockchains being base layer blockchains, where we're going to be building out the infrastructure of the future of financial assets, and there's a lot of value that's being stored on these ledgers, and so bad actors have huge economic incentives to try and cause faults within the system. So distributed consensus is how blockchains make decisions. It's how we verify transactions. It allows us to maintain the latest state of the ledger. And to understand how distributed consensus works, we'll talk about an old problem. So Lampert, Shotok, and Peace, in their 1978 paper, Reaching Agreement in the Presence of Faults, describe failures in distributed systems. They essentially there was another paper that was released before this called the Two Generals Problem, which was an unsolvable problem. And they referenced that within the system. But essentially, long story short, right, we have 9 different generals, right? You can see over here, we got 9 different, or these are 7 actually. There's 7 different generals, and they all want to attack this castle at the same time. Now, the thing is that it doesn't matter if they attack or they retreat, as long as they do the same thing together, right? As long as they do the same thing, they're not going to lose the overall battle. The main goal is to find a common decision and execute it together, not a specific decision. But there can be traitorous messengers or generals on the overall network. So this problem, it's an analogy for our blockchain network. Replace the generals with the nodes and understand that we need a way to establish trust within a distributed network, right? We need majority of these individuals to come to a consensus on a decision. Bitcoin uses proof of work as its consensus algorithm as a probabilistic solution to this problem, and so does Ethereum as of now. A quick note over here, Ethereum is moving to Ethereum 2.0. Phase 0 implementation will be September 5th of 2020. And then there's phase 1 and phase 2, which we're probably looking at somewhere around 2 to 3 years from now before it's fully done with all the specs that they have defined. So this is a much simplified version of solving the Byzantine generals problem, but to solve this problem, essentially, we need some sort of commander, right? And this commander is going to send V. In this case, we'll call it, we'll say V is attacking, right? So the commander is going to send attack to all the lieutenants, right? And then Lieutenant 1 is going to send attack to Lieutenant 2. And then, but the problem is that we have a malicious Lieutenant 3. And so Lieutenant 3 is going to send defend to Lieutenant 2. Now, when all these nodes come to consensus, the majority will be attack, attack, defend. And so we're going to attack because we have 2/3 consensus on the network. So the main takeaway over here is that it's a voting process. So Byzantine faults are in reference to any errors that show different data to different observers, and Byzantine in general is receiving contradictory information. A Byzantine failure is when the system is lost to a Byzantine fault, and when a system can tolerate these faults and still come to consensus, it's called a it's called Byzantine fault tolerant. So back to blockchains, we use consensus algorithms to elect a leader or the general, right, who will decide the contents of the next block. The leader or the commander is also responsible for broadcasting the block to the network so that peers can verify the validity of the block. So back to ETH, since we're going to be deploying contracts, we'll talk about ETH. In Ethereum, miners come to consensus about what happened overall for the state of the Ethereum world computer every approximately 15 seconds. And it uses a proof of work consensus algorithm. So essentially, for an individual to be elected as a leader, they must solve a specific mathematical problem. Since the hashing function is cryptographically secure, the only way to solve this problem is by brute force. So finding the solution to the problem is extremely difficult, but verifying the solution to the problem is incredibly easy. It allows us to cryptographically secure a particular amount of computation to generate the nonce output. If you guys want to read a little bit more about this, there's a paper. Let me think really quickly. There's a paper by Adam Back that was written in 1997 that introduced the hash cache concept, which is very similar to the proof of work concept, or it's at least a similar idea to Bitcoin's proof of work algorithm. Given data, we're trying to determine a magic number that, when added to the data, and when we say data, we'll say the blocks data, produces a hash below the difficulty, which is proportional to the expected time to find a block. Right. So essentially, the difficulty is a value that, based on the amount of hash rate that's on the network, will vary to essentially make sure that the block time is approximately 10 minutes in Bitcoin's case. And so the difficulty of the block affects the nonce, which is a hash that must be calculated when mining a block. So essentially, we're going to enumerate through all the possibilities until we find the answer. If we find the answer, we become the elected leader, and we get the Coinbase transaction as the miner as a reward for finding the solution to the problem. So now we're going to talk about there's three types of main nodes within the Ethereum network. We have full nodes, right? They process transactions passively while supporting the resilience of the network. Essentially, they just process transactions. They don't actually create new blocks. Mining nodes, these are the nodes who are all actively solving that proof of work puzzle. And they are actually processing transactions actively, and they're trying to, they're essentially they want to be the winner, to find the block first and propagate it to its peers. We have light nodes. Really quickly, light nodes only contain the block header, so you can verify transactions, and we use Merkle Patricia trees to store our transactions. Long story short, if we wanted to verify a transaction and it was in a list format and we had 16 elements within it, we would need all 15 transactions to verify whether that particular transaction was in that list, versus a tree where, if the case was 16, we would only need 4 different transactions to validate that it truly happened within the block. So simplified version of proof of work once again. And I think we're about hitting 9:37, so I want to actually start deploying some contracts. Before we do that, we'll talk a little bit about the Ethereum virtual machine. So the EVM is like the JVM, right? We write our code, we compile it, and it goes into bytecode, and we can deploy it, and it can run on the virtual machine, essentially. Complete machine, very simply stated, it can simulate any computer algorithm, with one exception, which is that it is limited by gas, right? We wouldn't want anyone to essentially write a for loop a while loop on the network, and then essentially have the whole Ethereum network just reaching a Stack Overflow eventually. So the EVM is a state machine. It processes bytecode that gets generated with assembly code, which in turn uses instructions called operation codes or opcodes. It allows code to be executed with the limitations of gas costs and gas price. So you can see over here. So there's two main types of accounts in Ethereum. There's externally owned accounts. The way I think about it is that these are user accounts, and then there are contract accounts. Contract accounts are accounts that are on the network itself. Remember, both accounts can hold a balance, and the main difference is that the contract account also has the code for the smart contract within it as well. Let's continue down this right here. And get over here. So Ethereum, there's basically two different, there's public testnets, and then there's obviously there's the mainnet, and then there are local testnets. So public testnets, there's Ropsten, which is a proof of work blockchain, very similar to the mainnet, Koban, Rinky, and Gorelli. And then as far as local testnets go, we have Ganache and Ganache CLI. We use local testnets because, I mean, imagine developing and then every 15 seconds, every 15 seconds or 20, you have to wait 15, 20 seconds every single time you deploy your contract that you're testing out. And so you're going to want to use some sort of local testnet. Both Ganache and Ganache CLI come from the Truffle, are part of the Truffle suite, and Truffle is a part of Consensus. So really quickly, right, what is the transaction flow, right? You have to be connected to a node to be able to broadcast your transaction. And so essentially, imagine you're on your browser, your console, or your laptop over here, and we're trying to make a function call. We can say vote for candidate, and then we can, but we have to be connected to a local full node, or at least, or we have to be connected to a local node. And then from there, remember that full nodes are not necessarily mining, right? So they cannot include a transaction in the next block, but eventually it will get into a mining node. I created this nice graphic over here that really represents exactly the transaction flow. So essentially, you're on your computer, you digitally sign the transaction, and you send it to the blockchain, and it goes into the first full node. So when the full node receives the transaction from a peer node, it places it within the memory pool. The transaction is executed on the EVM for validation. If it is successfully validated, transactions are broadcasted to peer nodes, and if it's invalid, it just is not going to propagate any further. And then from there, eventually the transaction will get into a mining node. When a mining node receives it, it's going to add it into its local memory pool. If that mining node happens to be the node that solved the proof of work puzzle, they're going to be awarded the Coinbase transaction. Essentially, they are going to they're going to order the transactions in any order that they want. Typically, they choose an order that's financially lucrative to themselves. And if they are deemed profitable and selected from the memory pool, executed on the EVM, and attempted to be added to the new block, right? If the new block is created, right, we found that problem, the related transactions are going to be removed from the memory pool, and it's going to be broadcasted out into the rest of the network, right? And then essentially the rest of the nodes, they are going to validate that particular block. So now let us deploy. Really quickly, does anyone have any questions? Okay. Everyone. All right. So we'll start out. I already have MetaMask. All right, I already have MetaMask installed on my computer, but I'd like for you guys to first go to remix.ethereum.org, right? So Remix is essentially, it's an online IDE for being able to write out your smart contracts really quickly in the browser. For the purposes of this demonstration, we are going to click over here, use previous version, click reload, and we are going to, it's going to load up over here our remix. So the first thing we're going to want to do is we're going to want to click on the top left, and we're going to want to say, we're going to create a ERC20 contract, right? ERC20.sol. ERC20 is the type of token that was used for the majority of the ICOs, and it only contains about 5 functions, but it has been extended upon, and you can read more about these different token standards by taking a look at the EIPs, or the Ethereum Improvement Proposals. So let's come over here and let's select a compiler version. We'll just use 0.5.11, and we are going to click over here on we're going to click on auto compile. All right, and then you can click on enable optimization if you'd like as well, and then click over here on run. Right, so now let's write out our smart contract. So the first thing we're going to want to do is we're going to want to define the compiler version. And so we do that by saying pragma solidity 0.5. Which one do we choose again? We chose 0.5.11. And we are going to start out by creating a contract, or if you're used to other object-oriented programming, think of that as like the largest class. So we'll say contract, and we're going to create an ERC20 token, and we'll open and close it up. So a few things, right? Our token, since we're trying to make a lot of money, we're going to have to give it a really nice name. So say string public name equals Starweaver coin. And since we're going to be having this trading on the markets, we'll also give it a trading symbol equals SC money, SCM. So notice how, so sorry, I don't think I mentioned this, but this right here is Solidity. Solidity is the main programming language for Ethereum. There is also Viper, which is in beta, which is much more similar to Python, but Solidity is what the majority of developers in the Ethereum space are using. So, and then we'll create a total supply, right? And we'll have it be UN256. And then we want to store 2 things, right? We want to store the balance of the users, as well as there's an idea of essentially creating an allowance, right? So if I want to allow my kid, I mean, I don't have any kids, but if I wanted to allow my hypothetical kid to use some of my money, then I would give him an allowance. So just for the purposes of speeding this process up, I will copy some of this code over. So we have balance of over here, which is a mapping, right? So address is a special data type that's specific to Ethereum, and it stores Ethereum addresses within it. And then allowance is a mapping of a mapping, right? So the address would be the owner, right, of the original wallet, and then the second mapping would contain all of the individuals who are allowed to spend on my behalf, and what is the amount that they're allowed to spend. So we will create a constructor function, right? Within our constructor function, for now, what we'll do is we'll just we'll give all of the initial supply to ourselves. So we say balance of, which contains all the balances, and we say message.sender. So message is essentially a variable that's available. It represents whoever is interacting with the contract, right? So Right now, well, the constructor can only be is only executed once at the time of deployment of the contract. Whoever deploys this contract will be the message.sender in this case. Then I will add in the transfer function. We'll add in a function to approve and a function for transfer from, right? And don't really worry about like this code. I know like it didn't get to Slack it to you guys or anything, but I mean these are standards, right? So all this code exists online. It's not really a matter of copying it down at this particular moment. And then we'll add in 2 different events. That's what's giving me all these errors. And voila, we've got our simple ERC20 token, right? So what does it do? Let's just quickly look at it one more time, right? What do we have? We are missing function balance of, but all right, that's fine for now. But so we can see over here, right, we have a function transfer, right, to the address 2 and whatever the value that we want to send it. We check, we have some sort of verification, and then we actually do the transfer. And then over here, we are emitting an event that you can attach event listeners to, and so you can listen for changes on a particular contract. We have approve, which is essentially giving an individual an allowance. And then we have transfer from, which is essentially allowing an individual who wants to spend their allowance to be able to spend it. So we technology, yeah, so it varies from place to place. So let us deploy this. Now, before we deploy this, we need to have a wallet and some sort of test ether. I'll actually paste this inside of here. You might have to format it a little bit. I pasted it inside of the chat. And so what you're going to want to do is you're going to want to go to MetaMask. I believe it's metamask.io, right? From there, you're going to want to click on Get Chrome Extension. You're going to download the extension. I'm not going to remove it for now because I keep some funny money on there. But essentially, you'll download it, and then this plugin will pop up over here on the right. When you open it up, you will see all the different networks that you can connect to. You got the mainnet, Ropsten, Coven, Rinkeby, like we talked about earlier, as well as you can connect to your local blockchain over here using localhost 8545 or Kalido. Right? Kalido is a blockchain as a service provider from Consensus. I believe it's part of Consensus umbrella, and essentially allows you to deploy private instances of, create your own private blockchains and manage it across multiple BaaS providers, or sorry, across multiple cloud providers. So if we click on Rinkeby, and to get some test ether, what we're going to want to do is we're going to want to click on deposit. After we click on deposit, on the bottom over here, you're going to see a test faucet. You're going to click on get ether. Once you have gotten to this website, you are going to click on Crypto Faucet. And from here, you need to request for test ether, right? Essentially, the reason why this process exists is because us as developers, or we would, if we had unlimited test ether, we would just spam the network. So what you're going to want to do is you're going to want to come over here and copy your address to your keyboard. And remember, this is directly from Rinkeby itself. So to get test ether, you need to either make a public tweet or a public Facebook post. You can obviously delete it as soon as you receive the tokens. So in my case, I'll just go to Facebook. I'll come over here and I'll make sure that my post is public, right? And I'll click post, right? And then I'm going to click on just now. I'll copy this link at the top and I will come back to the faucet. I'll paste it over here and I'll click on give me ether, which it's not going to work for me as over at Stanford teaching yesterday. And I used my Rinkeby faucet. So for you, it should show up as a green toast message at the top. And then from there, eventually what will happen is that the the test ETH will show up within your wallet. Now, you might be wondering, Siraj, you're talking about earlier, right? You're saying over here, you got to connect to a node somehow. So how does MetaMask do that, right? So MetaMask uses a service called Infura, right? And Infura is what's used on the back end for MetaMask to be able to connect to an Ethereum node. So definitely worth taking a look at. I believe they have free tiered nodes if you just want to, if you want to be able to connect to the mainnet without deploying your own node. So we have got some test ETH over here, right? Great. We're pretty rich in this virtual world, but we're gonna want to click. We're in Rinkeby now, and we are going to come and click on run. So notice over here, if everything compiled properly, your token contract name should show up. And there are 3 different environment variables over here. There's a JavaScript VM, which essentially emulates Ethereum within the browser. We have the injected Web3 provider, which is essentially MetaMask. What happens is that when MetaMask is loaded in, it injects the Web3 object into the window object of the DOM, so that your application is able to access is able to access what MetaMask has, right? And also to be able to access the nodes, right, that are connected in the back end with Infura. And the third would be Web3 provider, right? So if you want to directly just connect to an Ethereum node, you can do that as well. And one thing to just note over here is make sure that make sure you're not using HTTPS when you're trying to connect to the node that's not that. So otherwise you'll waste a lot of time. So let us deploy this token, right? So we're going to click on. We're going to create 100 coins or 1,000 coins. Or actually, forget it. We'll create 108 coins, all right? And we got this. We don't want to pass any value with our transaction. And gas, we didn't really get too much time to talk about gas, but gas is essentially the fee that needs to be paid in order to change the state of the transaction. So essentially, or changing the state using a transaction, and what you're paying for really is either the computational steps required to execute, and 2, the storage required. And I like the way I like to think about it is gas is kind of like a car, but one thing to note is that if you give too much gas, the network will refund you, but if you give too little gas, the state of your contract will revert back to the previous state, and essentially you will not be refunded your ether. So we are in the injected Web3, right? So we're connected to our MetaMask, and now let us click on deploy. Bam. So it's telling me over here it's going to cost me about 11 cents to deploy this basic contract. So let me click on confirm. And you can notice over here on the bottom, right, it popped up this link. So it's a link to what we call a block explorer, right? Block explorer allows you to essentially explore a particular blockchain. So you can see over here, this is my transaction on the Rinkeby testnet. We're still waiting for it to be added into the next block. In the meantime, you can see over here all the different latest transactions. You can see all the latest blocks, and you can see all the tokens. And the cool thing over here is that you can quickly switch from different networks to one another over here through this little drop down on the right. So, and we just got a confirmation message right over here. Hide this. Great. So we are great. So now we've deployed our contract, and we can see that our contract exists at this particular address, right? Remember, it's a contract account. And so let us now add, let's now see if we can have our tokens, right? So let's click over here on MetaMask. Let's click on main. And what we're going to want to do is click on add token. We're going to click on custom token, and we are going to paste in our contract address. Notice how the token symbol automatically was populated the moment that I put in the contract address itself. Click on next, and you can see that I have 108 SCM, right? 108 Starweaver, Starweaver coins, coin money, I guess. And so let's click on add tokens, and voila, we have created our first very basic token, and we have deployed it to the Rinkeby testnet. And now if I'd like to transfer this to anyone, if anyone has a wallet, please feel free to paste it over here inside of the chat. I'd be happy to send you some of my free tokens. I'm not really sure what they're going for right now, but to understand the value of any sort of item, I highly recommend going back and taking a look at the history of money.
We are Starweaver. Education you can bank on. For more information, contact us.